Hello, welcome to this video where I'm going to explain why integration works. In detail, I'm going to explain why the antiderivative gives me the area between the curve and the x-axis. How come it happens? How come it works? So suppose that I have the following function. That you can picture the area is going to be, well, for region 0 and 2, for example, is just going to be this shaded area, right? Now, the way I'm going to start by doing this is not just to go ahead and do the integration. I'm going to take another approach. And the approach I'm going to take is taking little boxes. So I take little boxes between 0 and 2. And they're going to have the height of some value of f of that value x. So for example, if it's f of 0.3, if I have x to be equal to 0.3, it's going to be f of 0.3, right? So for example. And that's going to be the way in which I'm going to make these little boxes. Now suppose, of course, if I make the area, if I add up the area of all these rectangles here, what I'm going to get is going to be bigger than the actual area. Realize that I have all these little extra parts here, right? That doesn't quite work. So what if I make more of these boxes? If I make double the amount of boxes, or 3 times or 10 times the amount of boxes, they would actually end up getting closer to this. And I would eventually get to the actual area between the curve and the x-axis. That is the general approach we're going to take. Let's take a look at it. So ultimately, this is what we're going to be doing. We're going to be making a lot of these boxes. How many? An infinite amount. So an infinite amount. What is the width of each one of these boxes going to be? Well, it's going to be the distance between what value, 0 in this case here, to the first value of x, and then to the next value of x. So the distance is always going to be the distance between each value of x. And I'm going to calculate the area of the box. I have to multiply times the height. And the height is going to be f of that value of x, right? In this case, it would be f of 0, or f of 0.3, or f of 0.7, or whatever it is. And this expression, when I make an infinite amount of boxes, is going to give me the area. And ultimately, what's going to happen is that proving that this thing here is the same thing as the antiderivative is going to be the big breakthrough in mathematics. And I'm going to prove that to you now, why that works, why the sum of all these little boxes actually come up and sum up to the antiderivative. How come that happens? So this is called the fundamental theorem of calculus, and it's a very important part of the history of mathematics. And we're going to be referring to this idea as the fundamental theorem of calculus. So let's go ahead for the proof. But before we do that, just a small notation sidestep. So differentiation, we've talked about it plenty of times. Now here's another way to define it. So here's a symbol, and the symbol is increment. Okay, so this is the delta, and it means increment of something. So if I have an increment on the y-axis, I'll put delta y. An increment on the x-axis will be delta x. So here's what we know. We normally have the derivative, right? So we have a value of x with its f of x here, right? So the coordinates will be 1, 1, x equals 1, f of 1 will equal 1. And if I go to 2, the delta x, the increment in x will be 1. And f of 2 is actually 4, right? So the increment in y would be 3. Great. Now you've seen this before. This should be familiar to you, the idea of the increment in y and the increment in x. And it should be familiar to you because it's the derivative, right? If I have my derivative, this part here, the top part, is f of x plus h here, minus f of x, minus f of x, so this is this increment here, 3. And here I have x plus h minus x, which ends up being h. And that's how I have my definition of the derivative. I can also write it like this. So that's another way to write the derivative. Okay, just instead of with f of x plus h, etc., I'm just putting delta y divided by delta x. And what goes to 0? The increment, the delta x goes to 0. Now this should make sense. This is just another way to write the derivative. And I hope you can see it clearly. We're going to use it now to prove the fundamental theorem of calculus. So let's do it. This is a simple proof. I think one you can reproduce easily, one you can understand easily. So I take any box on my graph. Remember this box is in my graph? Let me take just one box. And let's make that box a little bigger. So what am I going to have? I'm going to have an increment. An increment of what? I'm going to have an increment of the area. Because I just made that box a little bigger. Now, how much? How much bigger did I make it? Well, I make it bigger delta x, right? An increment of x. That's how much bigger I made it. And the height, well, it's going to be some f of some value c, which is going to be between x and x plus delta x, right? That increment, there's going to be a little box somewhere that its height is exactly going to be the area between between the curve and the x-axis of that increment of x. So these things are the same, right? So, well, for some value c, I multiply times the increment of x, and I get the increment of the area. So all I am going to do in this proof is take this dividing on the other side, and I end up with this. Great. Now, this is increment of the area divided by the increment of x is equal to f of some value c, and that value c, again, is between the value of x, the original one, and x plus the increment of x. Now, let's take limits. If we make the delta x go to 0, what do I end up having here? Hey, this is my definition of the derivative that I had earlier on. And what's going to happen here? Well, c is between x and x plus delta x. So if delta x goes towards 0, well, c is going to go towards x. So I'm going to end up having this, that f of x is equal to the derivative of the area. Now, there's a function a in terms of x that gives me the area under the curve, right? This is what this is saying. This increment of the area, right, is a function of x. So the derivative of that function gives me the original function. This is what's going on here. So what does that mean? Well, if we make the antiderivative of x, I'm going to get a function that gives me the area under the curve. And that's ultimately the proof, the easy proof for the fundamental theorem of calculus. Thank you for watching. Goodbye.